Hey everyone, welcome to On Track, an ongoing video series where we cover hot topics in PCB technology and designer interests. My name is Andy and I'll be your host as we dive into the latest industry trends and emerging developments in PCBs. If you're watching today's video or any others in the On Track series, chances are you're a PCB designer. And if you're a designer, you probably think you're a good designer. We won't dispute that, but even the best designer in the world doesn't know everything. In today's video focusing on Power Delivery Network, PDN, analysis, we'll dive into one of the crucial tools that even the best designers may not know to take advantage of. PDN analysis is all about optimizing current distribution in IC, package, and board level domains. The ongoing complexity of PCBs and their components themselves has turned PDN tools and analysis into a vital step in PCB design workflows. Signal integrity, thermal analysis, and overall board performance all benefit from a robust PDN program. You might be skeptical about adding PDN analysis to your design workflow, but the fact is, most board projects can't reach success without it. You can't eyeball your design anymore. For example, you might just go by designer intuition and/or adding a bit of headroom when choosing trace widths. You choose a width that looks good and go with that. What could go wrong? Well, how about a burning board? How about Swiss cheese power planes? Narrow grounding traces and overloaded vias can drive up board temperatures and make for undesirable current densities. It's not just your board at stake either. Poorly specified integrated circuits, ICs, can also become current-hungry hotspots. Let's take a closer look at a few key board components and the PDN best practices for each. Power planes. Traditionally, power planes weren't a focus of PDN optimization. You just added the layer and that was the end of it. However, the ever-increasing complexity of PCBs, especially in terms of adding layers, can unintendedly result in a poorly designed power plane. Check for bottlenecks and inconvenient discontinuities. Ground planes together with the power plane. The ground plane's relative voltage difference can be responsible for inductive effects on your PCB. They can create signal noise and add voltage disparities, both unwanted issues that are a pall on performance. You'll normally use a PDN analysis program to mitigate this problem, but there are a few design rules of thumb that help. Try using thinner boards with fewer layers, and when possible, keep the power plane at or near the board surface. Vias. Think of your vias like city storm drains in a rainstorm. Eventually, if it rains hard enough, the drain gets overwhelmed and the surrounding area floods. While your board can't flood per se, vias can turn into overheating pinpoint hotspots. They can even melt surrounding traces. You might normally design your vias for good EMI performance, but give a thought to how they relate to current as well. ICs. Oft overlooked as a source of PDN issues are your IC packages. We tend to look at them like black boxes. Inexperienced designers, especially, might just assume all is well when an IC is fed correct signal and voltage. That is, until they power up their prototype board and their ICs jettison themselves with a bang. With ICs getting faster and more powerful, you can't just rely on default nominal traces. Sewing these areas together is a good PDN analysis tool. Modern applications use the same visual CAD-like environment as your PCB design package, and some even integrate directly. Your PDN analysis tool will simulate current flows and tag areas of high current density. They may also include a basic thermal map, showing you how problem areas will have elevated temperatures. Add copper by expanding vias, traces, and planes where needed, and rerun the analysis to confirm results. V equals IR is the basic mantra of all PCB designers. Some, I bet, even have it tattooed on their biceps. But it's also a key element in PDN analysis, specifically in mitigating troublesome voltage drops on your board. With more and more ICs running at ultra-low voltages, even the slightest voltage disruption can create massive current changes. That means overloaded or possibly even fried ICs. This is the other half of the PDN mission, modifying and updating your design strategy to remove infrastructural design problems. As the V equals IR equation hints, Voltage drops have to do with current resistance or both. Fine-tune them, and dangerous voltage drops can be stricken from your board design. You can reduce high current densities by adding copper, widen traces, eliminate bottlenecks, supplement with extra vias. All these techniques spread current out and reduce voltage drops. On the other hand, resistances can improve by removing copper. Longer traces and convoluted pathways create more resistivity, worsening voltage conditions and pulling more current. Of course, by now you've spotted the conflict here. Just like managing current densities and hotspots, voltage drops also benefit from a good PDN analysis program. Your analysis should produce a map of your PCB voltage drops, allowing you to identify the responsible components. As for solutions, it's all about context. Shorter, think problematic traces might be widened, while a long, hot trace could be shortened and simplified. More than anything else, the design strategies, the consequences, the rules, today's takeaway needs to be the importance of a good PDN management. You can't just guess and check anymore, burning through prototypes and popping ICs like popcorn. You need a good PDN analysis tool working in conjunction with a program of design strategy improvements. Especially given the quality of recent analysis packages, what with the visual CAD-like environment and even design what-if analysis, incorporating PDN analysis won't be a burden. This is On Track. Thanks for watching. Until next time.